Okay, here we consider contingency table analysis. In particular, there's two hypothesis tests that we're going to look at, a test for independence and a test for homogeneity. And let me motivate this desire to test for independence through an example. This example is from Dr. Bob Henderson, a statistician at SFA. And there's a question of whether or not the severity of a specific skin disorder was related to the age of the patient. And so 216 patients were observed, and their age was observed, and their skin disorder was observed, and they were classified according to those two variables. So we have two qualitative variables that we are classifying on. You can see the age here is in 4 categories, 1 through 4, and the skin severity category there's 3 of them here: moderate, moderately severe, and severe. So the question is there some sort of we're interested, is there a dependency between the age of a patient and the severity of this particular skin disorder? Okay, and so with that in mind, we're going to talk about a contingency table. Now, in general here, we think of ourselves having 2 categorical variables, one called a row variable and the other called a column variable. Okay, and so the column variable, I'm going to write out here the actual table. I'm going to have a column variable, and it's going to have 1, 2, all the way up to little c levels. So for the example that we just looked at, there's 4 levels for that column variable. The row variable in general is going to have 1, 2, all the way down to r levels for that variable. And when we summarize data on 2 qualitative variables, this is called a contingency table. Okay, so we have this table here, and what we observe in the table, the notation we use here is N11. That's the number of observations that were classified according to level 1 for both the row and the column variable. N12 is the number of observations classified on the first level of the row variable and the second level of the column variable, and so forth. Here, N1C, that's the number of observations classified on the first level of the row variable and the cth level, or the last level, of the column variable. We can have here N21, also N22, and so forth. And down here we could have NR1 all the way here to NRC. Okay, and so in general, any cell within this contingency table tells you how many were in, how many subjects were classified according to those respective classes for the column variable and the row variable. Okay, and what we can do is we can actually look at various totals here. We can look at row totals, and that would be specified here. R1 would actually be the sum of N1J. J would go from 1 to C. Okay, it's the sum of all those values in the first row. And I can do that for every row. So I can have R with the subscript little r. That is the row total for the rth row. And that's going to be NRJ. J is going to go from, again, 1 to C here. Okay. I can also have column totals. All right. So I can sum down this first column, and I'm going to call that C1. C1 is going to be the sum of Ni, Ni1 in this case, and I is going to go from 1 to little r. Okay. And that I can have a C2 all the way up to a CC. Okay, capital C representing the column total. Subscript tells us what level we're at for that column variable. And if I sum across either the row totals or the column totals, then I get my grand sample size here. So that's I'm going to call that N. N is the sum. J goes from 1 to R of Rj, or the sum C goes from 1 up to little c here. The sum of the column totals, either one of those will give you sum of the column totals or sum of the row totals. Either one of those will give you the total sample size. Okay, so with this kind of data, we can look at what's called a test for homogeneity or a test for independence. We're going to first consider a test for independence. Okay, when you think of two variables here, you can think of dependence of variables would tell us that maybe one variable has some value for predicting the other. Okay. Now, when you look at sample data, there usually appears to be some degree of dependence. And what we're going to look at is a particular chi-square test that assesses whether this perceived dependence is just a fluke from the sample data, or actually the result of compared to real dependence there. And so we're looking for statistical significance here. So this test for independence here, what we're going to do is we're going to assume we have a random sample of size n, where each observation is classified according to two categorical variables. The hypotheses, a little more, they're more wordy than what we've had for previous hypotheses. We're just going to state here that H0 is that the row and column variables are independent, and HA is that the two variables are dependent, or they're associated. Notice we don't say anything about how strong the association is, or that sort of thing. We're just saying they're dependent, and we'll look later at a measure of strength for the dependency. But to test this hypothesis, we have the following test statistics, and what we need, we're gonna ultimately come back to this chi-square test statistic, similar to what we saw before, where you take the observed amount minus the expected amount. But the expected amount, let's think about how we would get that. The expected amount is n times pi ij hat, and pi ij hat assumes independence, and when you do that, then you have Ri over n times Cj over n for that point estimate, which turns out to be Ri times Cj over n with that first n in the numerator. So that's our expected cell count. What we do again is we look at the difference between the observed count and the expected count, square that difference, divide by the expected count there, and then add through all the cells in our table. That's what that double sum tells us to do. This follows an approximate chi-square distribution with R minus 1 times C minus 1 degrees of freedom for large samples. Again, our rule of thumb here for large is that the expected count is larger than 5 for every cell. Okay, so that's what we're deeming as a large sample for this sort of situation. And we're going to reject if our chi-squared value is large. In other words, if there's a large discrepancy between what was observed and what was expected under the null hypothesis, we're going to reject that chi-squared value. Okay. I will say here there is another measure of dependent, or a measure of dependency, not just this particular chi-square test, but there's this measure of dependency called Pearson's contingency coefficient, and the book uses the notation T equals to the square root of chi-squared observed divided by chi-squared observed plus n. And so it turns out that if t is equal to 0, well, when t is 0, in the way this is designated here, that implies that the two variables are independent. Okay, and when t is 1, that would imply that there's complete dependency. Complete dependency between the two variables. Okay, so the closer t is to 1, the higher the dependence. The closer t is to 0, the lower the dependence there. So we will make use of that particular coefficient. Back to this example though, let's actually look at the hypothesis test. So what we're interested in is the column variable age, is it independent of the row variable skin disorder, or skin severity, skin disorder severity. So the null hypothesis would look like this, that age and severity are independent, and the alternative is that age and severity are dependent. Okay, dependent there. Okay, so we're going to use our chi-square statistic. In fact, most of it's been computed for us within the notes here, and I want to illustrate some of that. So looking at these counts, just so we're clear, this count right here, say the count 32, that's N12. Okay, N12 is the number 32, and that is the number of people that were in age category 2 and had a moderate skin disorder, was the rating for their skin disorder. Now that's what was observed. Now the expected counts are given in this other table over here. So in this same cell here, this is in this case, this is E12. That is going to be R1 times C2 over N. Okay, so you're going to take, what's R1? R1 is 70. All right, let me give myself some space. 70, then times what's C2? C2 is 81. And you divide that by N, which is 216. You take that ratio, you get 26.25. Okay, so this sort of thing needs to be done for every cell. You take the observed, and then you have the expected, and so what you do ultimately, if you look back at our test statistic, we take the observed minus the expected, we square that. Okay, so that's what's done in this table here. His notation has O. We've got N sub ij. O is observed, but N sub ij there, and this would be N sub ij as well. So we take here we're going to take 15. If you take 15 minus 7.778, square it, then divide by 7.778, you're going to get 6.706. This is going to be the contribution to that chi-square statistic for the cell moderate age category 1. Alright, so you do that for each of these cells. You take the observed minus the expected squared over the expected, and then you add them all up, and then this is the observed chi-squared statistic. That's the chi-squared statistic. Okay, so you can verify the math there, but we've added all of those values up. And so what does that mean? Is that a statistical significant result? Do we have evidence to conclude that the two are dependent? That's what we're asking here. Now, this is a very vague alternative hypothesis. It just says they're dependent. It doesn't. So, specifically what the dependency looks like, how strong is the dependency, it just says they're dependent. Okay. So, moving on here to actually computing the p-value, we'll just get to the cut to the chase. The p-value here would be the probability of seeing a chi-squared bigger than what we saw, which was 27.13. Okay, and if you want to reference your chi-squared distribution, here's a picture. We need the degrees of freedom. Remember, the degrees of freedom is r minus 1 times c minus 1. So I've got 2 times 3, which is going to be 6. And over here is, we'll say 27.13. If you look in your book at the chi-square distribution with 6 degrees of freedom, you'll see that there is an upper value of 22.46, whose area under the curve to the right of that upper value is, or that area is 0.001. And so my picture is clearly not to scale, but you get the idea here. That this probability, the area under the curve to the right of 27.13, has got to be less than the probability that the chi-squared is greater than 22.46, which from the table is 0.001. So our p-value is less than 0.001. It's very small here. So hence, one would reject H0 and accept H1, accept the alternative, or HA as I have it specified there. So there's some sort of dependency between those two variables. And the data here, when you look at the contingency table, a nice graphical representation here is this stacked, or not stacked, but side by side bar graph, and it kind of gives you a picture of, yeah, there does seem to be some dependency between those two variables, but this chi-square test formally addresses that. Okay. Next, we look at what's called a test for homogeneity.